Chapter 10, Acids and Bases. Probably do this slideshow in two segments. As you can see, there's only 25 slides, but there is some math in here, so I'm not going to rush right through. Hopefully you've got molarity under control. So in a previous chapter, we looked at calculating molarity, doing moles over liters. That will come back to play in this chapter. So in this chapter, what we're going to focus on is acids and bases, specifically Bronsted-Lowry acids and bases. We'll look at the strengths of acids and bases. To do that, we'll look at the ionization of water and then see how that plays out on the pH scale. After that, we'll focus in on reactions of acids and bases, basically looking at neutralization. For the Chem 110 course, we'll look at titration as well. And then we'll finish out with buffers. All right. So properties of acids. Acids typically taste sour. So we tell you kids don't try this at home. But realistically, if you enjoy soda pop like colas, Coca-Cola for instance, that has some phosphoric acid in it, or maybe you just like citrus fruit. So all of our citrus fruits have citrus acid in it. So you probably are partaking in some acids there. Acids will conduct electricity. Some are considered strong and some are considered weak electrolytes. And if you don't remember what that means that they will ionize and fall apart in water. And if they're a strong electrolyte, they will completely ionize. And if they're a weak electrolyte, they will partially ionize. Acids will react with metals to form hydrogen gas. They will change indicators. Typically we use litmus paper, and so litmus paper will turn red in the presence of an acid. And of course we'll say they react with hydroxides to form water and a salt. And of course hydroxides, that means bases. So acids will react with bases to form salt and water. Now some properties of bases. They react with acids to form water and salt, just like acids react with bases. Bases will taste bitter. Okay, so things like milk of magnesia, whenever your stomach's upset, you call mom, is what the commercial says. Or Tums, Rolaids, right? They usually have a chalky, bitter taste. These days, I know you can buy flavored Tums and Rolaids, so you may not ever use the original, but if you do, then you'll know that they have sort of a bitter flavor to them. Typically soaps will feel slippery, right? So don't try this either, but realistically we do want you to do that. We want you to use soap and shampoo to clean yourself at home. Of course, in these days, we don't worry about that too much since we don't see you. We're all online, so you don't really have to worry about whether or not you're doing it or not. They also can be strong or weak electrolytes. So again, bases ionize. Either they completely ionize if they're a strong electrolyte, strong base, or they'll partially ionize if they're a weak base. And bases will change litmus paper to blue. So acids will change it to red, bases to blue. All right, now Arrhenius definitions. Arrhenius gives us some definitions for acids and bases, but we tend to gloss over that and go right to the Bronsted-Lowry, and that's simply because the Arrhenius base is OH only hydroxides. But as it turns out, other compounds can be basic in nature as well, and so we're going to account for that by using Bronsted-Lowry definitions. So by their definition, we have an acid as a proton donor, and a base will be a proton acceptor. And so while a hydroxide readily accepts a base, readily accepts a proton, there are plenty of other bases that will also accept a proton that are not hydroxide. So Bronsted-Lowry basically says that acids and bases then have to come in pairs. So if we have something giving away a proton, we have to have something there that will neutralize or accept that proton. So for instance, HCl would be a strong acid. It means it's going to completely dissociate. So when we dissolve HCl in water, it gives its proton to the water. So here you can see we're going to take HCl, it's a gas, so we're going to bubble it through a container of water, and that water is going to be liquid water. As it does that, the proton goes from the HCl to the H2O. And notice we have a plus charge now on our what used to be a water, now has an extra proton. And we have the chloride ion off to the side here. Now water is a base. In this case, it's going to make what we call the hydronium ion. So the hydronium ion is now going to be the acid. It's accepted the proton. Now remember, we said they come in pairs, and so our general equation then won't always have HCl in it. It's going to have any anionic acid. So we represent that with HA. Now, this is a monatomic here, right? We have one hydrogen, or monoprotic, if you will. The A is simply anion. So it can be any anion we choose. Okay? When we mix that with water, we're going to form H3O plus and A minus. Now, when we're looking at Bronsted-Lowry definitions of acids and bases, we just said it was a proton donor and a proton acceptor. So here we can see that HA is going to be our proton donor. And here, H2O is going to be our proton acceptor. Now, when we get to the other side of the equation, they're going to switch roles. H3O plus now has the extra proton. That means this can now be the proton donor. A minus has that negative charge. That means it can accept a proton. And so now it's got basic nature. Now it'd be confusing if I say which one is the acid and which one is the base, if we don't come up with a way to denote what's going on the product side. And the way we do that is we use the word conjugate. So the acid and the base are always on the reactant side. And then once that proton's been transferred, on the product side, we now have the conjugate acid, which is the H3O plus, and the conjugate base, the A minus. Now remember, the H3O plus used to be the water, and the A minus used to be the acid. So the acid becomes the conjugate base, the base becomes the conjugate acid. Now we're representing this with a double-headed arrow, which means we've set up an equilibrium. Now we can do this equilibrium with bases as well. So for our general format, we're going to take a base and we're going to put that in water. And now we're going to see water can act as the acid. The base will accept a proton from the water and give us BH+. Since we pulled one of the hydrogens off the water, we're left with hydroxide. And that's why we say OH is typically going to be a base. And now we see that OH minus on this side will actually be the conjugate base. So we had a base. We're going to use water as the acid. Once that base accepts the proton, it becomes the conjugate acid. The water then, which was the acid, now becomes the conjugate base. Now water can act as an acid or a base. Okay, that makes water a Zwitter ion. Z-W-I-T-T-E-R, Zwitter. All right, our example here will be ammonia. And again, I don't have to have a hydroxide on there, and that's why we don't like the Arrhenius definition too well. It's easier to understand with the Bronsted-Lowry definition. The NH3, the ammonia, can now accept a proton and make NH4+. That's now my conjugate acid. The water is going to lose a proton, and so now it's OH minus, and that will be our conjugate base. Now, how do we keep track of strength? Well, strong acids and bases are strong electrolytes, and as I mentioned earlier, that means they fall apart completely. Weak acids and weak bases will not completely ionize. Now, when we talk about strength with an acid, or we talk about strength with a base, we're talking about their electrolyte capabilities here. Are they completely falling apart, or are they not completely falling apart? Now, if I increase the concentration, whether it's a weak acid or a weak base, that will also have an impact on the strength. However, if it's a strong acid or a strong base and it's concentrated, then you can imagine we're going to have lots of ions in the water, which means we're going to see more chemical reactivity. We can also have diprotic, triprotic, dihydroxide, trihydroxide. And so if I have that happening, then I'm also going to see even more of it going into solution, right? So magnesium hydroxide, there's two OHs there. So when it dissolves, I get both of those OHs to come off. So I'm doubling up the hydroxides based on the concentration itself. Now, polyprotic acids, basics, some compounds can give more than one ionizable hydrogen. So for instance, if we have HNO3, we would call that monoprotic. H2SO4, sulfuric acid, is going to be diprotic. H3PO4, phosphoric acid, is going to be triprotic. Now, are you seeing the pattern here? It's the hydrogens out front, right? If I have one hydrogen out front, it's monoprotic. If I have two hydrogens out front, diprotic. Three hydrogens out front, that's right, triprotic. So you can imagine if I have four hydrogens, what will that be? Tetraprotic? Probably something along those lines, right? All right, so measuring strength. In order to get to understand strength, we have to look at ionization. Ionization is going to be reversible. So in other words, if I go back to my general equation, I've got that double-headed arrow, and we call that an equilibrium. Well, what that means is that it's basically a reversible reaction, and it's happening at the same time. So I have HA going to H plus A minus, and at the same time I have H plus A minus going back to HA. Okay, now there's an equilibrium constant for that. And so we can look at math and figure out what we call a rate. So how much of it is going in one direction, how much of it is going back to the other, and how does that work out for us? We call that Ka. So K sub A. Now K just means it's a rate. So whenever we see Ks in chemistry, it's a rate. Or it could be potassium, so you got to be careful. But typically when we're talking about equilibrium, we're saying it's the rate. Now the Ka is equal to this H plus in this weird bracket. These weird brackets, that means concentration. So if we go back and we look at molarity, that's where this is going to come into play. So we would put the molarity in to this calculation. So we would say the concentration of H plus times the concentration of A minus divided by the concentration of HA. It's basically going to be the products divided by the reactants. That's what we do. Now, this becomes valuable because if I have a stronger acid, then I'm obviously going to have more products, which means Ka should go up, right? If I have more up here multiplying through and a smaller number in the denominator, then larger Ka. Now, I don't want you to worry about having to do the math here because you're not. What I need you to be able to understand is that these Ka values are logged in a book, right? So we can look these up on the internet, or we can use the CRC manual, which we keep in the lab, and we can look up the Ka values for different acids. And what we'll find is that the larger that Ka is, the stronger the acid is. So Ka is taking into account the type of acid, whether it's strong or weak, right? So whether it's going to easily ionize or not. It's taking into account how many H's are coming off. Is it monoprotic, diprotic, or triprotic? And it's taking into account the overall concentration of the acid. So whether you used 1 molar or 15 molar. Okay, so it's taking into account all three things. And then we tabulate that. So we have a whole list of concentrations of 1 molar acids, and it tells us what the Ka is. And that tells me how strong the Ka is, right? The larger that Ka, the more products it's going to make, the stronger it's going to be. Now, what about bases? Bases can also do the same thing. We can set up the same general equation, and guess what? We can also set up the same math, except now instead of saying Ka, we're going to look at Kb. The process is the same though. It's products over reactants. And here we're going to ignore the water because typically whenever we put any of these things in water, there's so much water there that if I worry about the concentration on the water, everything else becomes way too small to deal with. So we're going to ignore the water. Okay? The stronger the base, the more it dissociates. We saw that with the acid. So the nice part is it's the same style game. And the larger the Kb is, the stronger the base is going to be. All right. Do some practice here if we want. I won't ask you to do this on a test. It would just be to make sure that you understand what we're doing with concentrations and products over reactants. So if I asked you to write the expression for HNO2, or what is the Kb for NH3, again, you would start with just the reaction and then put the concentration of the products divided by the concentration of the reactants. All right. Now, what's an easier way to keep track of strength? Well, a lot of us are familiar with pH. And pH, it's pretty easy to then say, oh, if it's a pH of this value, then I need to be concerned that it's a strong acid, or it's a weak acid, or it's a strong base, or it's a weak base. So the way we get to the pH scale is to look at the idea that ionization of water. So in other words, water ionizes. So if I just look at a bottle of water, in that water, if I could magic school bus us down and take a look, what I'd see is that water is falling apart into H plus and OH minus. Now, this is called the self-ionization of water. And let's keep it real here. It's a really, really, really small amount. So if we did magic school bus ourselves down and we're like floating through looking at all the different things in the water, we're mostly going to see water molecules. Every once in a while, we might catch a little glimpse of an H plus and an OH minus. They'd probably stay pretty close to each other, but we wouldn't see that many of them. So it's only a small amount. In fact, it's about 1 times 10 to the negative 7 molar. Think about that for a second. 1 times 10 to the negative 7. That's 6 zeros after the decimal before you get to the 1. Okay, so that's really, really, really small, and that's a neutral solution. So yeah, if I increase the concentration, I'll get that number to be a little bit larger, but we're still talking a very, very, very small amount. Now, in water, we have what's called the Kw. Now, we've seen this K thing before. We saw Ka and we saw Kb. And K, remember, is just an equilibrium constant. It's just measuring the rate at which these things do these things. Kw is going to be called the ion product constant, and it's going to be a constant for every aqueous solution. Doesn't matter what's in there. The minute the water is the solvent, Kw has to have a set value, and that's always going to be 1 times 10 to the negative 14. So if you can't tell, this right here actually belongs over here, and it is a superscript. Okay, and so Kw is always equal to 1 times 10 to the negative 14. That's going to account for all the acid and all the base that may be in our solution. Okay. All right, so there's my double-headed arrow, H2O going to H plus and OH minus. And I just told you that Kw is going to be constant in every aqueous solution and has a value of 1 times 10 to the negative 14. Now, the last thing I have to tell you about this is that notice the dependency of H plus and OH minus. They have to equal a constant. That means if H plus goes up, what has to happen? Right, OH minus has to go down. We've seen this relationship a few other times in chemistry. So if the concentration of H plus goes up, then the concentration of OH minus has to go down. If the H plus goes down, the OH has to go up. And as long as we know one, we can always determine the other. And this is how we're going to figure out if we have an acidic solution or a basic solution. You see, if the H plus is greater than 10 to the negative 7, then we're going to have an acidic solution. That means the OH minus is down. If the H plus concentration is less than 10 to the negative 7, we call that a basic solution. Now, when I look at these, I can get a little confused pretty quickly. For instance, 10 to the negative 2. Is that larger than 10 to the negative 7 or smaller? And hopefully you say it's larger. Now, in order to get to pH and use these really, really, really small numbers or these really, really, really big numbers, we'll use what we call logarithms. All logarithms are is a method of using the power of 10. And this way we can take a really, 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 really big number, or as in the case that we're dealing with right now, a really, 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 really small number, and make it manageable using a shorthand tabulation. So the equation we're looking at when we look at pH is pH is equal to the negative log of the H plus concentration. Now on your exam, you're going to have a calculator. So I'm not going to expect you to memorize how to do these logs, but you're going to have to figure out how to use your calculator. So we're going to go through that. Let's take a look at a neutral pH solution here. This way we know the answer has to be 7, because remember, we said that it has to be 1 times 10 to the negative 7 is how often that hydrogen breaks apart from the hydroxide. And we developed Kw from there just a few slides ago. Now what I want to do is use the same value to figure out how to use my calculator. Now, if you're using your phone, you're most likely going to have to turn it sideways so that you get all the extra buttons. For instance, you're going to need the log button. Now, our logarithms here are going to be base 10. And typically, whether you're using your phone or like a TI-80 something or a Casio or whatever other brand, there's really only 2 ways to do this. So I'm going to go through both ways. The first way is if your calculator is a standard digital calculator, non-alphanumeric. So it only does numbers, no letters, no syntax, no type of typing in. So in other words, if you have like a big TI-80 something, then you can actually do syntaxed. And so there's going to be a different method for that. Okay, now so this is going to be for your digital. Now, whenever we're trying to do pH on a digital output, so on a digital calculator, we're going to take 1 times 10 to the negative 7. Now how we type that in, there's a few different ways. On my phone, what I'm going to do is I'm going to hit 1 and then EE. That automatically takes care of times 10 to the. Then I'm going to hit 7 and then negative. Okay, so that was 1 E E. Now again, that represented my times 10. Then I'm going to type in 7, and then I'm going to hit the plus minus key and make that a negative. Then I like to hit equals, and that's going to give us a value of 0.00000001. Now I'm going to hit the log, and then I'm going to hit the plus minus key again. And then when I hit equals here, I get 7. Now again, that's the first way to use your calculator. Now, if you have a TI-80 something or an expensive Casio, then chances are it's going to be able to go alphanumeric. All right, so now if it's alphanumeric for our second method, what we're going to do is type it in exactly like we see it. So we're going to type in negative, then we're going to hit the log button, and it's going to go log, and it's going to automatically open a parenthesis. Now at this point, just like before, we have a couple different ways we can input these numbers. You can do the same thing though. Go 1 EE 7 plus minus. Close the parenthesis and then hit execute. It should give you 7. All right, if you're still struggling with your calculator, make sure you get a hold of me, or maybe look at the instruction manual, or maybe talk to, if you have a math course, the math instructors are usually pretty knowledgeable with these things too. Probably know the calculators better than I do. This is the biggest function we actually use in 110, but we do a few other things with them in 150. So I have a little bit of knowledge on them. But again, if you have access to a math instructor and you'd rather ask them, or if you have a friend who's got a big TI something and they're pretty good with theirs and you want to get help from them, that's cool too. But you have to be able to do logarithms in your calculator. Okay, it's a must do. All right, I think we're going to pause here. So we've learned how to use our calculator. We're 25 minutes in, so it's a little bit of a long segment. So I think we'll take a break here. Then we'll do some practice problems with our pH scale, see how that works out, and then we'll talk about neutralization, and then we'll finish out with buffers. So stay tuned for the following segments.